Your program ran fine yesterday. Today Python can't find the package you installed. Here's the real thing. One line of Python, one import, and a wall of red text. No module named requests. But you remember installing requests, so what happened? You're not imagining anything, and none of this is your fault. Welcome along. By the end of this chapter, you'll know exactly what breaks a working Python project, why nothing crashes when the breakage happens, and the shape of the thing that fixes all of it for good. And here's the one that really stings. 2 projects on the same laptop. You install a package for the first project, you never once open the second, and the second project stops working.
How?
Hold that question, because the whole chapter is the answer. To see why one project can break another, we need to look at what's actually sitting on your machine. Picture a shelf. Every piece of code you install arrives as a sealed parcel, and the label on the parcel says 2 things: a name and a version number. The name almost never changes, whereas the number changes constantly, and that number is where all the trouble starts. Every parcel comes from the same place, one enormous public warehouse called pip, where anybody can put a parcel on the shelf, and anybody can take one down. So when you type pip install, pip is where your machine goes looking. Now watch what pip actually does. I asked for one parcel.
For arrived.
Read the lines pip is printing out. Markdown at py, pigments, dirl. Nobody asked for those 3. And look at the strange little bits of text beside each name, because those are the reasons. Rich can't run without pigments, so pip fetched pigments too. Code that other code needs in order to run at all is called a dependency, and dependency is the single most important word in this whole course. Rich depends on pigments, which means pip must fetch pigments too. Markdown at py depends on dirl, so dirl arrives as well. That's 2 levels deep from one install, and nobody told you. Look at the order pip chose. So far, everything works, which is exactly why the next part catches people out. Here's the bit nobody mentions. There's only one shelf. Not one shelf per project, one shelf for the entire machine. Your invoice app and your report tool are completely separate pieces of work, written months apart, and both of them reach into that same shelf for the same parcels. And now the 2 projects want different things. Your invoice app was built against Pigments 2.21. Your report tool needs the old 2.0 because the report tool was written back when 2.0 was current. Same parcel, 2 numbers, 1 slot, which means one of those projects is about to lose. So pip does the only thing pip can do and narrates the whole business itself. Attempting uninstall. Found existing installation. Uninstalling. Successfully uninstalled. Pip lifted the parcel your invoice app depends on straight off the shelf, and pip never asked the invoice app what it thought. Then pip prints these 2 lines, one after the other. Pip says error, and names the exact incompatibility pip has just created. And 4 lines later, in the same breath, pip says successfully installed. And then nothing happens. That's the part one want you to sit with. Run the code that's now broken and Rich prints its text perfectly happily, because Rich only reaches for the missing piece on certain code paths. There's no red text, no traceback, no moment of discovery, which is exactly why the damage goes unnoticed. The shelf is simply wrong now, and the shelf stays wrong until some other line of code, on some other day, finally trips over the missing piece. That's why this costs people an entire afternoon. By the time the pain arrives, the command that caused the pain is long forgotten, and that command told you it succeeded. One command would have told you, and almost nobody runs it. Pip check reads the shelf and says, in one plain sentence, which parcel is now wrong for which project. And the loud error from the very beginning? Same shelf, different symptom. The requests parcel is real, requests exists, and you genuinely did install requests. Requests is just sitting on a different shelf from the one your program is standing at. So the loud error and the quiet one share a single cause, the shelf. So, what would actually fix all of this? Before I answer, one quick check that the important word landed. You asked for 1 package, and 4 turned up. What do we call the 3 nobody asked for? Have a think, and pause the video here if you'd like a moment. Ready? They're dependencies, code your code needs in order to run. Here's the answer, and honestly, it's almost embarrassingly simple. Give every project a shelf of its own, and put a wall between the shelves so that nothing crosses over. Your invoice app keeps the new pigments, your report tool keeps the old pigments, and neither project can reach across and touch the other one's shelf. That folder of parcels, belonging to exactly one project, has a name, a virtual environment. So, why does almost nobody keep one? Because of the ritual. You make the folder. You switch the folder on. You carry around in your head which folder you're currently in, because the terminal barely tells you. You switch the folder off when you leave. And the first time you forget any single one of those steps, you're straight back on the shared shelf without knowing. Unless something performs the ritual for you. There's a tool called UV, and removing that ritual is the entire reason UV exists. The folder gets made, used, and forgotten on your behalf every single time, and you never think about any of it. One command instead of 4 steps. We install UV in the next chapter. So, to recap, a package is a parcel with a name and a number, and asking for one parcel quietly brings others along. Your machine has one shelf. Every project reaches into that shelf, and one slot holds exactly one version. And when 2 projects disagree, the last install wins, nothing crashes, and you find out weeks later. Next chapter we install UV, and I'll show you why a tool whose job is installing Python can itself be written in Python. A tool whose job is installing Python. Written in Python. Do you see the problem? This is the whole installation. One line, pasted into a terminal, on a machine that has no Python on it whatsoever. 15 seconds later UV is there, and working. By the end of this chapter you'll understand every part of what that line just did. Welcome back. This chapter gets UV onto your machine, and more importantly, it explains why installing UV works so differently from installing anything else in the Python world. Start with the problem, because the problem is what makes the solution make sense. Here's something about pip almost nobody says out loud. Pip is a Python package. Pip lives inside a Python installation, in a folder called site packages, right alongside every other package you've ever installed. Ask pip where pip is, and pip will tell you. Which means pip can never fix a broken Python because pip needs that Python in order to start. Break the interpreter, and pip goes down with the interpreter. Now, none of that is a bug, and none of it is pip's fault. Living inside Python is simply what pip is. So UV is built the other way around. UV is one compiled program, written in Rust, sitting beside Python rather than inside Python. UV needs no interpreter to start, which is exactly why a single line of curl works on a bare machine, and why in a few chapters UV can download an entire Python for you on demand. There are several roads onto your machine, and they all end at the same binary. Mac and Linux use curl. Windows uses PowerShell. Homebrew works, and so does Wingit. And then there's the 4th road, which is the one to avoid. Why is that 4th road a trap? Because pip puts UV inside a Python environment, and managing Python environments from the outside is UV's whole job. Delete the environment, and UV disappears along with the environment. Worse, UV can no longer update itself, because a package cannot overwrite its own file while Python is holding that file open. Now let's read that install line properly, because you should never paste something into a terminal you cannot read. Curl fetches a file over the internet. -L follows redirects. -S stays quiet. -S still shows real errors. -F fails properly on a bad response instead of saving the error page. Then the pipe hands that file to sh, which runs it. That's it. Download a script. Run the script. On Windows the shape is identical. PowerShell fetches the script with IRM and IX runs it. Same binary, same destination, different shell. And now the step that trips up literally everybody the first time. When you type a command, your shell doesn't search your whole computer. Your shell walks a short list of folders in order and runs the first match found. The list is called path. The installer put UV in a folder near the end of the list, then added that folder to your shell profile. But your open terminal read the profile once, back when the terminal started, and no shell rereads a profile on its own. So the first thing almost everybody sees after installing UV is command not found, and almost everybody assumes the install failed. The install did not fail. Close the terminal, open a fresh one, and UV is right there. The version line is worth reading properly because 3 separate facts live in it. First, the version number, then the exact commit the binary was built from, then the build date, When you report a bug or follow along with a tutorial, the commit hash is what tells another person precisely which UV you are running, down to the day. UV keeps its own things in 3 folders, and it will tell you where all 3 are. The cache is where downloads are kept, so the second install is instant. The tool folder holds programs you install. The Python folder holds interpreters UV downloaded for you. These live in different places on Windows and on Unix, and UV knows which. Quick check. Of those 4 roads, why is pip install UV the one to avoid? Pause here and have a proper think about it. Ready? Because pip puts UV inside a Python environment, and managing those from outside is UV's whole job. And because UV is only ever files and folders, removing UV takes 3 commands and no control panel at all. Clear the cache, delete the tool and Python folders, delete the binary. Nothing else on your machine ever knew UV was there. One last thing the installer deliberately does not do. UV does not touch your system Python, does not modify any environment you already have, and does not put a bare Python command on your path. Everything UV installs lives in UV's own folders, which is why removing UV leaves absolutely nothing behind. So, to recap, pip lives inside Python, so pip can never rescue a Python that's broken. UV is one compiled binary that sits beside Python, which is why a single line installs it on a bare machine. And when the terminal says command not found, open a new terminal. Next chapter, you run a tool you have not installed, and I show you the stopwatch that explains why UV feels the way it does. What if you could use a program without installing the program? Watch this. Rough is a Python linter, and rough isn't on this machine anywhere. I type one command, rough runs, rough checks the folder, and then rough's gone again. Nothing was added to any project, and nothing at all was left behind. Welcome back. This chapter is about borrowing tools instead of owning them, and about the small warehouse on your own machine that makes borrowing feel instant. Start with the command itself, because 2 spellings of it exist, and knowing that saves confusion later. First, a small thing that saves confusion later. UVX is not a separate program at all. Typing UVX rough is exactly the same as typing UV tool run rough. Not similar, identical, and the documentation says so plainly. Both spellings are worth knowing, because older tutorials tend to use the long one. So, what actually happens when you run one? UV builds a tiny throwaway environment off in the cache, drops the tool into it, runs the tool, and then simply stops caring about that environment. Your project isn't touched, which means nothing lands on your path either. You won't find a new command sitting there afterwards. Because nothing is being installed, you can pin a version without committing to anything at all. Adding at 0.3.0 runs that exact release. Adding at latest always fetches the newest one. Neither choice changes a single file in the project you happen to be standing in. 2 flags turn UVX from a nice trick into something you'll use constantly. Sometimes the package and the command have different names. The package height_py installs a command called http, so UVX height_py would look for a command called height_py and fail. -- from tells UV which package to fetch, and the word after it is the command to run. And -- with adds extra packages into that throwaway environment for the one run. So you can hand a tool a plugin it doesn't ship with, use the pair together once, and leave no trace of either afterwards. Better still, a tool can come straight out of a Git repository, which is how you try somebody's unreleased branch without adopting it. Same shape as before, fetch, run, forget, except the parcel came from a repository rather than the warehouse. So, why does any of this feel instant, when the first run clearly had to download 10 megabytes? I timed it. The first UVX rough, on a completely empty cache, took 5.792 seconds. That's 10 megabytes fetched, unpacked, and run. The second, seconds later, took 0.294. Same command, same machine. The only difference is that the parcel never had to leave town twice. That local store is called the cache, and the cache is the real answer to why UV feels the way it does. I'll open it up properly in a later chapter, because it deserves one. For now, just hold on to the shape. The first run pays, and every run afterwards doesn't. A tool can also be run under a Python you do not have. Passing --Python 3.12 makes UV fetch that interpreter, build the throwaway environment on top of it, and run your tool there, while the Python you normally use sits completely untouched. And if you want to see where all of that actually happens, look inside the cache. Every throwaway environment UVX has ever built is sitting in one folder, keyed by exactly what was asked for, which is why asking for the same thing twice costs nothing the second time. Occasionally you'll want to force a fresh copy, because a tool has published a fix and the cached parcel is still the old one. -- refresh throws that cached copy away for a single command, and only for that command, so everything else you've built up stays exactly where it is. If you've used pips, all of this will feel familiar because pips does the very same job and has done for years. What's different is that UV already owns the cache, already owns the resolver, and already owns the interpreters, so borrowing one more tool costs UV almost nothing to arrange. Quick 1. You run UVX rough inside a project folder. Afterwards, is rough a dependency of that project? Pause here and decide for yourself before I say a word. Ready? No, the environment lives in the cache and your project never heard about it. One honest limitation before we finish. Because every UVX run builds its own little environment, a tool you reach for 20 times a day pays a small startup cost every single time, and none of those tools end up on your path. When that starts to annoy you, the answer is the next chapter. So, to recap, UVX and UV tool run are the same command. UVX builds a throwaway environment, runs your tool in it, and forgets the environment. And the second run of anything is nearly free, because the cache already has the parts. Next chapter, the tools you actually want to keep, and the one misunderstanding that catches everybody who installs one. You installed the tool. Your terminal says command not found. Both are true. Here's the whole thing happening. UV installs rough. UV reports installed one executable, and then UV warns you in the very next breath that the folder holding rough isn't on your path. Most package managers leave a beginner to work that out alone. Welcome back. Last chapter you borrowed tools. This one is about the handful you use every day and why keeping those is a different decision entirely. So when should you borrow, and when should you keep? There's a simple test. Borrowing is right when you reach for a tool now and then, because paying half a second occasionally costs nothing. Keeping is right when you type the name 20 times a day, because then you want the command itself, not a prefix in front of it. UV tool install is the other mode. Same bay, but now the tool is bolted to the floor. UV builds it a permanent environment of its own, then puts one small file on your path that points at it. That one file is what makes the bare command work. You can see both halves. UV tool dir holds a whole environment per tool, complete with its own Python. The bin folder beside it holds nothing but the shims, one tiny file per command, and that's the only thing your shell ever sees. Which brings us straight to the thing that trips everybody up on day one. The warning fires because the shim folder isn't in your shell's list yet. UV won't silently edit a shell profile behind your back, so the first install says so and waits for permission. One command fixes the list permanently, and a fresh terminal picks the change up. On Windows, a shim is a real executable file rather than a symbolic link, which is a Windows detail rather than a UV one. On macOS and Linux, you get a link instead. Either way, one file per command, and removing that file is how a tool goes away. Now the misunderstanding. This one is worth stopping on because almost everybody hits it. You install rough as a tool. Then you open a Python file in your project, type import rough, and Python says no such module exists. Nothing is broken and nothing went wrong. Rough lives in rough's own environment, and your project is a completely different environment. So if your code needs to import a package, that package belongs in your project, and we'll do exactly that in a couple of chapters. Tools are for things you run. Dependencies are for things you import. Keeping those two ideas apart will save you an enormous amount of confusion. Finally, living with the tools you've kept. For commands cover everything. List shows what you've kept and what each one gave you. Upgrade takes one tool forward, or all of them at once. Uninstall removes a tool and its shim together. And UV tells you plainly when there's nothing to do. One difference is worth watching for. When borrowing a tool, you pin the version with an @. When keeping one, you use the ordinary equals syntax instead. The mismatch catches people constantly because the two commands otherwise look so alike. And one rule straight from the documentation, worth repeating exactly. Tool environments are not meant to be edited by hand. If a tool needs a plugin, Reinstall the tool and name the plugin with -- with, so UV writes the plugin into a receipt file and remembers the pairing next time. Here's a habit worth forming early. Pin the tools that decide whether your code is acceptable, because a linter that quietly upgrades overnight can fail a build nobody touched. Pin rough, pin the formatter, and leave the harmless conveniences floating on latest. A kept tool also gets its own Python, which matters more than it sounds. Upgrade the Python you use for your own work, and rough carries on running against the interpreter rough was installed with, because nothing in rough's environment depends on yours. And because every tool has a private environment, two tools that need incompatible versions of the same library simply never meet. That's the Chapter 0 problem solved once more, quietly, in a place you weren't thinking about. One more flag earns its keep. Adding -- isolated alongside -- refresh builds the environment from scratch and ignores everything cached, which is how you prove a failure is really the tool's fault rather than a stale copy sitting in your depot. Quick check. You install rough as a tool, then try to import rough in your project code. What happens? Pause the video here and think it through properly first. Ready? It fails because the tool lives in its own environment and your project is a different one. So, to recap, borrow a tool you reach for occasionally and keep the one you type all day. Installing a tool gives it a private environment and puts one shim on your path. And a tool you can run is never a package your code can import. Next chapter, something genuinely surprising, a single Python file that installs its own dependencies and runs from nothing in under 2 seconds. One Python file. No project, no setup, no install step. It just runs. Watch the clock on this one. A single file sits on this machine, and Rich is installed absolutely nowhere. I run the file. UV reads the file. UV builds whatever the file asks for, and the output appears on screen. 1.8 seconds, from nothing at all. So where did Rich come from? Welcome back. This chapter is about the smallest useful thing in the whole of UV, a single file that carries its own dependencies and needs nothing else on the machine to work. Start at the simplest possible version, then work up to that demo. Typing UV run, and a file name runs that file. Where a project already has an environment, UV'll reach for that one. Where a package is missing, you can lend the script one for a single run with -- with, exactly the way you lent a tool a plugin 2 chapters back. Lending works, but lending is fragile because the knowledge of what the script needs lives in your head and in your shell history. Send the file to a colleague, and your colleague gets the same module error you got. The fix then has to put that knowledge inside the file itself. So, how do you write requirements inside a Python file that Python itself will ignore? There's a real Python standard for exactly this, and it's beautifully simple. Put a block of comments at the very top of the file, opened by // script and closed by // Python skips the entire block because comments are comments and the interpreter doesn't care what's inside them. UV reads the very same block and builds an environment out of the contents. You never have to type that block by hand. Running UV init -- script writes the block for you, and UV add -- script edits the block in place afterwards. Which means adding a dependency to a lone file is the same gesture as adding one to a whole project. Now here's the part that makes people sit up. My init command asked for Python 3.12, and 3.12 was not on this machine anywhere. UV simply downloaded an entire Python, 21 megabytes of interpreter, and carried on without stopping to ask. And none of that would be possible without what Chapter 1 explained. UV is a binary standing beside Python, which means UV can go and fetch a Python. A tool written in Python couldn't manage the same trick because it'd need an interpreter before it could start looking for one. 2 more things, and then the file becomes genuinely portable. Put a shebang line at the very top and the file becomes runnable on its own. Mark the file executable, type /demo.py, and your operating system hands it straight to UV, which reads the header and does everything else. No Python command typed anywhere. Now, the header names what the script needs, but not the exact versions, which means 2 people can still end up with slightly different parcels. Running uv.lock -- script freezes those versions into a companion file beside the script, and from then on everybody who runs the file gets an identical set, the same guarantee a project lock file gives you. One rule does catch people out, so it's worth saying plainly. When a file carries an inline header, the project around the file is ignored completely. The documentation says the project's dependencies will not be used, which means a script sitting inside a project still gets a private shelf, built only from that script's own header. There's more that fits in the header than a package list. Requires Python sets the interpreter, exclude newer freezes the whole resolution to a date, and a tool table can carry per tool configuration. All of it still comments, and Python still ignores every line. And because everything lives inside the file, the second runs nearly free. UV keys that little environment on exactly what the header asked for, so as long as the header stays the same, the depot answers and nothing is fetched again. Quick check. A script has an inline header naming rich, and it sits inside a project that depends on HTTPX. Can the script import HTTPX? Pause here and think it through before I answer. Ready? No, the header wins, and the project is ignored entirely. This is genuinely useful in real life. A one-file utility you can email to somebody. A build step in a repository that needs 2 libraries nobody wants in the main project. A snippet in a bug report that actually runs on the reader's machine. All of it from 4 comment lines. So, to recap, then, a block of comments at the top of a file tells UV what the file needs, and Python ignores those comments completely. UV writes and edits that block for you. And if the Python you asked for is missing, UV fetches it rather than refusing. Next chapter we stop letting Python be something you install by hand, and let UV own every version on your machine instead. How many Pythons are on your laptop right now? Most people guess wrong. I asked this machine and the answer was 3. One from an installer years ago, one from a science distribution, and one that came with the operating system. None of them knew about the others. That's a completely normal laptop, by the way. Welcome back. This chapter hands the whole problem of installing Python over to UV, so you never download an installer from a website again. First, the distinction that makes everything else make sense. Interpreters get sorted into 2 piles, and the split matters because it decides what UV is allowed to change. A system Python was already on the machine when UV arrived, so UV will happily use one, but will never modify it. A managed Python is one UV downloaded itself into UV's own folder, which means UV can add and remove those freely. And the headline behavior, straight from the documentation, UV will automatically download Python versions when they are required. You've already watched that happen in Chapter 4. No installer, no website, no wizard. The version you asked for simply turns up. You can name several versions at once, and you can name implementations other than the usual one. PyPy and graalpy are alternative Pythons with different performance characteristics, which means the same code can behave quite differently on each, and UV fetches either with exactly the same command. Now the command you'll actually type most often. Running UV Python list prints the whole rack. Every line is a version and the right-hand column is the interesting bit. Either a real path, meaning that interpreter is already here, or the words download available, meaning UV can have it in a few seconds if you ask. One detail is worth knowing before you rely on any of this. The interpreters don't come from python.org. Instead, UV uses a project called Python Build Standalone, which produces portable builds designed to run from any folder at all. That portability is exactly why UV can drop an interpreter into its own directory and have it work immediately. And here is the part that makes a project reproducible rather than merely lucky. Running UV Python pin writes a tiny file called python-version into the folder you're standing in. From then on, every UV command run in that project uses the version named in that file. Commit the file, and your colleague gets the same interpreter without being told. That file gets searched for in the folder you're standing in and in every parent above it, which means a pin at the top of a repository covers every project inside, and a pin inside one project overrides the one above. Nearest wins, which is the rule you'd expect anyway. 2 behaviors here surprise people, so let's say both plainly. First, UV uses the first compatible version, not the newest one. If your project needs 3.10 or better, and 3.10 is sitting there, UV takes 3.10 and does not go looking for anything shinier. Second, installing a Python with UV doesn't put a bare Python command on your path. That's deliberate, because silently replacing the Python command on somebody's machine is exactly the kind of surprise UV refuses to spring. If you genuinely want that, --default asks for it explicitly. There's a related file, worth not confusing with the pin. The pin says which Python to use. Requires Python over in pyproject.toml, says which Pythons your code is allowed to run on at all, a promise to everybody else, rather than a choice for you. Every command that runs Python takes the same flag, which is genuinely useful when you're checking whether a bug is version-specific. Add --python and a number to UV run, and the whole thing runs on that interpreter instead, without changing anything you've pinned. And once UV owns your interpreters, that chapter 0 mess starts to clear on its own. Every project names the version it wants, UV fetches whatever is missing, and nobody ever downloads an installer from a website and forgets which folder it went into. Quick check. Your project needs 3.10 or newer, and both 3.10 and 3.13 are installed. Which does UV pick? Pause the video here and commit to an answer before I say it. Ready? 3.10. First compatible, never newest. Managed Pythons come and go like anything else UV owns. Uninstall removes one, list shows what's left, and none of it ever reaches the interpreters your operating system depends on. Which means you can try a release candidate on a Tuesday and be rid of it by Wednesday. So, to recap, UV separates interpreters it merely found from interpreters it downloaded and only ever changes the second kind. A one-line file pins a project to a version and travels with a repository. And UV takes the first compatible version, not the newest one. Next chapter we finally make a real project and read every single file UV writes, line by line. One word makes a project. But what did those 6 files actually do? One command, UV init, and a project name, and a project exists. 6 things appeared, none of which you typed. Most tutorials skip straight past this and start installing packages. We're going to read every single file instead because a project you can't read is a project you can't fix. Welcome back. This chapter builds a real project and reads every line of it, so nothing in your own folder is ever a mystery again. Start with the file everything else hangs off. Pyproject.toml is the standard way a Python project describes itself, which is why every modern tool reads it and none of them need convincing. Not a UV invention, in other words, a Python standard that UV happens to follow properly. For sections, and we'll take them one at a time. Name and version identify the project. Description and README are for humans. Authors is written from your local Git configuration, so check what landed there before you publish anything. That line goes out into the world with your package. Requires Python is a promise, not a preference. It says which interpreters your code claims to work on, and UV refuses to add any package that can't satisfy it. So this one line quietly shapes every dependency decision that follows. Dependency starts as an empty list, and next chapter fills it. Then build system, which tells anyone packaging your code which machinery to use. Notice the constraint written there is less than 0.13.0, even though the documentation page shows it without the trailing 0. Trust the file. Now, a warning about every older tutorial you're going to find. The documentation says it plainly. Prior to version 0.12, UV did not define a build system for applications by default, which means a tutorial recorded last year shows a different set of files from the ones you just got. Nothing is broken, the tool moved. There are 4 shapes UV can make, and the flag you pass decides which. App is the default, meaning something you run. Lib is something other people import, so UV puts your code under a src folder to keep the import path honest. Packaged gives you a command name. And bare writes almost nothing, because sometimes you'd rather decide everything yourself. And the rest of the files quickly because none of them hide anything. .python-version is the pin from last chapter, written from whatever interpreter UV chose. Main.py is a one-line starter file, so the project runs the moment it exists. README is empty and yours to fill in. And git ignore already excludes venv, which means you cannot accidentally commit an entire environment to your repository. 2 more files turn up later without being asked for. The venv is the project's own shelf, and uv.lock is the exact list of what's on it. Neither is something you create. Both appear the first time you add a dependency or run anything. One command deserves special attention, and you'll type it constantly. uv-run does the whole ritual from chapter 0 on your behalf. Check the environment exists, make it if not, make sure the packages match, then run your code inside it. For steps, invisible, every time. If you asked for a packaged project, one more section appears. Project scripts maps a command name to a function in your code, and after that uv-run followed by that name runs your function directly, which is how a Python project turns into something with an actual command. It's worth knowing that uv-init will happily take over a folder you already have. Point it at a directory with code in it, and uv writes only what's missing, which means adopting an existing project is one command rather than an afternoon of copying files around. One more thing worth doing on day 1. uv-init made a Git repository for you, and now is the moment to decide what belongs in it. The project file, the pin, and the lock file all go in. The environment folder does not, because uv already excluded it on your behalf. And if you'd rather not have a Git repository at all, --no-vcs skips it. Small thing, but worth knowing before uv creates a repository inside a repository and your version control starts behaving strangely. Quick check. You just ran uv-init, and there's no venv folder anywhere. Did something go wrong? Pause the video here and decide for yourself before I answer. Ready? No, the environment appears the first time uv actually needs one. So, to recap, pyproject.toml describes your project and every modern tool reads it. Requires Python is a promise that constrains every package you'll ever add. And the environment and the lock file arrive by themselves the first time uv needs them. Next chapter we finally add a dependency, and I show you why uv add does not do the thing almost everybody assumes it does. Everyone thinks uv add pins the version. It does not. Here's what really happens. I asked for rich, and uv wrote rich greater than or equal to 15.0.0. Read the operator carefully. Not equals, greater than or equal to. So that line is a floor rather than a pin, which raises an obvious question. If pyproject doesn't pin the version, what does? Welcome back. This chapter adds packages properly, reads every symbol uv prints while doing it, and shows you the graph uv draws of your own project. Start with the command, then the thing it wrote. uv add does 4 jobs at once. uv resolves what your request implies, writes the requirement into pyproject.toml, updates the lock file, and installs into your environment. One command where the old world needed 3 separate ones and no environment to activate beforehand. So, why a floor rather than a pin? Because pyproject.toml describes what your project can live with, and pinning there would stop anyone depending on your package from ever upgrading rich. The exact version gets recorded somewhere else entirely, the lock file, which is the next chapter. You can of course write the range yourself, and uv-will respect whatever you ask for. Quote it though, because those symbols mean something to your shell too. Pin exactly with double equals, cap an upper bound with less than, or allow only patch releases with a squiggle equals form. Now the symbols uv prints while it works, because they carry real information. 3 markers and each one means something different. A plus sign marks a package that arrived. A squiggle marks one that changed or got rebuilt. A minus marks one that left. Once you can read all 3, uv's output stops being noise and starts being a report you can act on. Watch what happens when a package leaves. I added httpx earlier, and httpx brought 6 friends along. Removing httpx takes all 7 away, because uv knows nothing else in the project was asking for those 6. Chapter 0's install, run backwards. And now the command that draws your project for you. uv tree prints the whole dependency graph. Your project at the top, everything it asked for underneath, and everything those things asked for underneath that. But look carefully at this particular tree, because there's something in it worth stopping on. Pigments appears twice. Once because rich needs pigments, and once because pytus needs pigments too. 2 packages asking independently, neither knowing about the other. And yet your environment holds exactly 1 copy, at 1 version, shared happily between both. Which is exactly the collision from chapter 0, except this time the collision worked out. Both packages happen to accept the same version, so a single copy satisfied both askers. When 2 packages don't agree, uv refuses rather than overwriting, and that refusal deserves a chapter of its own, coming shortly. Last piece. Not every dependency is the same kind of dependency. PyTest is a test runner. Your code doesn't need PyTest in order to run. You're the one who needs PyTest in order to develop. So it goes in a development group instead, and anyone installing your package as a library never receives it. There are two more shapes worth knowing. Named groups let you separate docs tooling from lint tooling from test tooling. And optional dependencies become extras, things a user of your package opts into by name, rather than receiving whether they want them or not. 3 more sources are worth knowing about, because not everything you'll depend on lives on PyPI. UV will take a package from a Git repository from a folder on your own disk or from a plain URL, and each one is written into pyproject so your colleague gets the same source you did. One flag deserves a mention on its own, because it's about how you work rather than what you install. Editable means UV points at a folder instead of copying it, so a change you make in that folder is live immediately, with nothing to reinstall. And when you want a newer version of something, UV's upgrade package flag moves exactly one thing forward and leaves the rest of the lock file untouched. Which matters, because upgrading everything at once is how a working project becomes a debugging session. Quick check. UV add rich wrote rich greater than or equal to 15. Your colleague clones the repo next month, when 16 is out. Which version do they get? Pause the video here and think it through before I answer. Ready? 15 because the lock file decides, not that range. So, to recap, UV add writes a floor rather than a pin because pyproject describes what your project can live with. Plus, squiggle and minus tell you what was added, changed, and removed. And UV tree shows you where a shared package is needed twice. Next chapter, the thing everyone told you to make and nobody ever explained, what a virtual environment actually is, in 6 lines of a text file. Everyone told you to make a virtual environment. Did anyone say what one is? It's a folder. That's the entire answer, and I want to say so before anything else, because the words virtual environment sound like something clever is going on. Nothing clever is going on. Here's one, opened up, with not a single mystery inside. Welcome back. You've been using one of these for 4 chapters without being told what it is. Let's fix that properly because this is the idea everything else in Python packaging rests on. Open the one file that decides everything. Here is the entire configuration of a virtual environment. 6 lines. Home says which real Python this folder borrows from. Implementation and version info record which one. UV notes the version that made the folder. Prompt is the name your shell shows. And then the last line. Include system site packages, set to false. That single line is the isolation. The line tells Python that while this environment is active, don't go looking at packages installed on the machine. Look only inside this folder. 1 word, and 2 projects can never see each other's shells again. Home is worth a moment too because home explains why these folders stay small. The environment contains no copy of Python at all. Home points at a real interpreter elsewhere, and the folder simply borrows the one it points at. Which is why a fresh venv weighs a few megabytes rather than a few hundred. Now the 2 folders inside, which are where things actually are. Bin holds executables, the Python for this environment, plus any commands your package is installed. On Windows, the very same folder is called scripts, which is the single most common reason a copied and pasted command fails to work. Same contents, different name. And lib leads down to a folder called site packages, which is where every package you install ends up. Open site packages, and you find more folders. Rich is a folder. Pigments is a folder. There's no database, no index, no registry, only directories with Python files inside them. Which brings us to activation, and to why you have not typed it once in this whole course. Activating an environment does one small thing. Activation puts the bin folder at the front of your path, so typing Python finds the venv copy first. That's the whole trick. No process starts and nothing is registered. Your shell's search list simply gains 1 entry at the front. Which also explains why forgetting to activate is so easy and so quiet. Nothing tells you off. Your shell simply finds the machine-wide Python instead, installs land on the shared shelf, and you find out weeks later, which is precisely the Chapter 0 problem, arriving by a different road. So UV run replaces activation entirely, which is why you've never typed activate once in this course. UV run finds the environment, makes sure the packages match the lock file, then runs your command inside. Correct every time, with nothing to remember and therefore nothing to forget. How does UV find the environment? A fixed order, and it's worth knowing. An explicitly activated environment wins. Then a conda prefix. Then a venv folder here, or in any parent directory above you. First match wins, which is why UV run works from a subfolder. There's a command for making one directly when you want environment without a project around it. uv.venv builds the folder, tells you which interpreter it borrowed, and prints the activation line for your shell. Same folder, same 6-line file, just made on purpose rather than on the way past. You can also choose which Python the folder borrows and give the folder a different name. Both are useful when you're testing whether a bug is version-specific because two environments side by side beat one environment you keep rebuilding. One more file in there is worth naming. Dist info sits beside every installed package and records what version arrived and what that package needs, which is where uv pip show gets its answers from. Nothing is being looked up remotely. It's reading a text file 6 folders down.
Quick check.
Which single line in pyvenv cfg is the thing that keeps two projects apart? Pause the video here and picture the file before I answer. Ready? Include system site packages, set to false. One line, and that is the isolation. One last practical note. Never commit a venv. The folder is large, the folder is specific to your machine, and the folder rebuilds from the lock file in seconds. UV already wrote a git ignore excluding it, so committing one takes deliberate effort. So, to recap, a virtual environment is a folder with a 6-line text file in it. One of those lines, set to false, is the whole isolation. And UV run finds and checks that folder for you. So activating one is a habit you can simply stop having. Next chapter, the file that makes your colleague's machine match yours exactly, down to the individual bytes. It works on your machine. It fails on theirs. Same code, same command. Your pyproject says rich greater than or equal to 15. You installed it in March and got 15.0. Your colleague clones the repo in June, when 16 is out, and gets 16. Same file, two different sets of packages. So, what stops the drift? Welcome back. This chapter is about the file that makes two machines identical, and about the one UV behavior that genuinely startles people coming from pip. Start by separating two words that get used interchangeably and mean different things. Locking is deciding. Given your requirements, UV works out one exact set of versions that satisfies all of them, then writes the decision down. Syncing is doing. UV reads that decision and makes your folder match it. Two separate jobs, and keeping the two apart is what makes the whole arrangement reliable. You'll almost never type uv.lock yourself, though, because every command that touches your environment locks first. Adding a package locks. Running your code locks. Syncing locks. So the file stays correct without anybody maintaining anything, which is rather the point of the design. Open the file, because there's a field in it doing more work than you'd expect. Here's a real entry. A name, a version, where the package came from, and then a hash, SHA-256, followed by 64 characters. The hash isn't decoration. A version number tells you which release arrived. A hash tells you which exact bytes arrived. Those are genuinely different promises. Why does the difference matter? Because a version number can in principle be re-uploaded, and because any download can be corrupted or intercepted on the way. A hash catches both problems. If the bytes arriving don't match the recorded hash, UV refuses to install rather than hoping for the best. The lock file is also universal, which is a genuinely unusual property. One file covers every platform, Windows, Mac OS, Linux, several Python versions, so a colleague on a different operating system resolves from your file rather than needing one of their own. And now the behavior that surprises everybody who arrives from pip. I installed Typer behind UV's back, using the pip interface. Then I ran a plain UV sync. Watch what happened. UV uninstalled 3 packages nobody asked it to touch. Not a bug. Sync is exact by default, and exact means the folder must match the lock file, with nothing extra sitting alongside. Which sounds alarming, and is precisely the point. If UV left extras alone, your environment would slowly fill with packages nobody ever recorded, and sooner or later one such package would be the reason something broke. Exact means the folder always tells the truth about the file. 3 flags matter on a build machine. Locked fails if the lock file is out of date, which is exactly what you want in continuous integration. A refusal beats a helpful silent update. Frozen uses the file as it stands and never re-resolves. And no sync locks without touching your environment at all. One more thing's worth knowing, because it surprises people in the opposite direction. New releases are ignored until you explicitly ask for them. A newer rich comes out, and nothing happens, no automatic upgrade, no quiet drift. You ask, or the version stays exactly where it is. A fair question at this point. When does the lock file actually go stale? The answer's narrower than most people expect. Changing a requirement so the locked version no longer qualifies makes it stale. Loosening a constraint that still allows the locked version does not, because the recorded answer is still a valid one. It's also worth saying plainly what the lock file is not. Nobody edits the file by hand. uv.lock is generated, regenerated constantly, and any hand edit gets overwritten by the next command you run. Treat the file as output, read it, review it in a pull request, and never type into it. And the diff is genuinely useful in review. Because uv.lock is text, and every entry carries a version and a hash, a pull request bumping one dependency shows exactly which packages moved and which stayed put, considerably better than trusting a summary line in a commit message.
Quick check.
You pip install something into a UV project, then run UV sync. What happens to that package? Pause the video here and decide before I say anything. Ready? UV removes it because sync is exact and the package is not in the lock file. So commit the lock file. That one file turns works on my machine into works everywhere. It's plain text so a code review can actually read it, and it costs you nothing at all because UV keeps the file correct on your behalf. So, to recap, locking decides one exact set of versions and writes them down with their hashes. Syncing makes your folder match, exactly, removing anything that isn't recorded. And nothing upgrades until you explicitly ask for it. Next chapter. What happens when two packages want versions that cannot both be true, and how UV explains its own refusal in plain English. Two packages want different versions of the same thing.
Now what?
Chapter 0 ended with pip overwriting one package with another and reporting success. Here's UV, handed the same impossible request. UV refuses, and then UV explains, in ordinary English, exactly why. Read it, because that paragraph is the whole chapter. Welcome back. This chapter is about how a package manager decides, what it does when no decision exists, and how to read the paragraph it hands you when that happens. Start with the easy case, so the hard one has something to be compared against. Picture one line, with every released version of a package laid along it. Each package wanting that thing lays a bracketed range across the line. Wherever all the brackets overlap, any version inside the overlap will do, and UV picks one. That's resolution, and honestly, there's nothing more to it. In that example, foo will take anything from 1 upwards, and bar needs 2, or better. Both are satisfied from 2 onwards, so UV takes 2.0, the lowest version inside the overlap that also happens to be the highest available answer that both accept. Now the case that actually teaches you something. I asked for PyTest 9.1.1, and at the same time for plug-E below 1.0. PyTest needs plug-E at 1.5 or above. Those two brackets sit on opposite ends of the line and never touch. No version of plug-E can satisfy both, so no answer exists. And here's the part worth slowing down for. UV doesn't merely announce a failure. UV walks you through the reasoning one step at a time, because PyTest depends on plug-E above 1.5, and because your project depends on plug-E below 1.0, we can conclude the two are incompatible. A proof, written in English, which tells you where to look. Either loosen your own pin on plug-E because you may not really need one below 1.0, or loosen the pin on PyTest because an older PyTest might accept an older plug-E. Two ends of one line, and you get to choose which one moves. There's a hint at the bottom of that error too, and the hint deserves a warning. UV offers -- frozen, which skips locking entirely and writes the requirement down anyway. Occasionally, that's the right move, but frozen stores the problem rather than solving it. Read the hint as an escape hatch, never as advice. 3 settings change how UV chooses, and each exists for a real reason. By default, UV picks the highest version each constraint allows, which is what you almost always want. Lowest picks the earliest instead. And lowest direct takes the earliest for the packages you named yourself, while still taking the highest for everything they dragged in. Why would anyone want the lowest? Because your pyproject claims your code works with rich 15 or newer, and nobody has ever checked that claim. Running your tests on the lowest allowed versions is the only way to find out whether the promise you published is actually true. One more distinction is worth knowing. Resolving a project produces a universal answer, valid on every platform at once. The pip interface resolves for the machine you happen to be standing on instead. Same resolver, two different questions, which is why one produces a portable lock file and the other cannot. Those little conditions are called markers, and markers are how one file stays correct everywhere. Colorama is only needed on Windows. .toml is only needed before Python 3.11. So a single lock file records which packages apply to whom, and every machine reads its own answer straight out of it. A practical note on reading these messages, because they can get long. Start at the bottom. The last line is always the conclusion. Your requirements are unsatisfiable, and every line above it is the working. Read upward until you hit a package name you recognize, and that's usually where you can act. There's a third kind of conflict that catches people out, and Python itself causes it. Sometimes no version of a package supports the Python you promised to support, so the refusal mentions requires Python rather than any package version. The fix is usually to raise your floor. And there's a deliberate way to freeze time, which is genuinely useful when you're bisecting a problem. Exclude newer tells UV to resolve as though nothing had been published after a given date, so you can reproduce exactly the set of packages a colleague had last March.
Quick check.
UV says no solution found and names two constraints. What's the fastest way forward? Pause the video here and think it through before I answer. Ready? Loosen one of the two brackets it named, because the message tells you exactly which two are fighting. So, to recap, resolution is brackets on a version line, and an answer exists wherever they overlap. When no overlap exists, UV refuses and explains the reasoning step by step. And resolving at the lowest allowed versions is how you check whether your published floors are honest. Next chapter, the honest answer to why UV is this fast, and I close the stopwatch loop I opened back in chapter 2. 5.7 seconds. Then 0.29. Same command, same machine. I promised in chapter 2 that I'd explain this properly, so here we are. 9 chapters ago you watched the same command take 5.792 seconds, then 0.294. Nothing was optimized in between. So, where did 5.5 seconds go? Welcome back. This chapter is the honest answer to why UV feels the way it does. Not a benchmark graphic, but the actual mechanism and what it costs you in disk space. Start with what actually gets kept, because the answer is more than you'd guess. The cache is a folder of buckets, and each bucket holds a different kind of thing.
Downloaded archive.
Built wheels. Source distributions. Whole environments, from chapter 2. And every bucket carries a version number in its name, which means several UV releases can share one cache without ever confusing each other. The built wheels bucket is the one that matters most. Some packages contain C code that has to be compiled, and compiling can take minutes. UV keeps the compiled result, so the second time you need that package on this machine, there is nothing to compile at all. Each kind of thing is keyed on whatever identifies it. A registry download is keyed on the URL and the response headers. A Git dependency is keyed on the commit hash, which is exactly right. A branch moves, a commit never does. And a local folder is keyed on the modification time of its files. And when the default key isn't right, you can say so. Cache keys in pyproject lets you tell UV what a rebuild actually depends on, a particular file, a git commit, an environment variable, so your builds neither rebuild pointlessly nor skip a rebuild they needed. So the cache explains the second run. But the first run was fast too.
Why?
3 other things are doing work here. UV is compiled, which means no interpreter has to start up before anything can happen. UV downloads and installs in parallel rather than one package after another, so a slow package never blocks a fast one. And where the operating system allows it, UV hard links files into place instead of copying them. Hard linking deserves a sentence because it sounds like cheating and isn't. A hard link is a second name for a file that already exists on disk. So installing a cached package into a new environment writes almost no bytes. The file is already there and the environment just points at it. Now, let's be careful about numbers, because this is where tutorials get sloppy. Astral's homepage says 10 to 100 times faster than pip. That's their claim, and I'm attributing it rather than repeating it as fact. Their own benchmarks page, at the time of recording, carries no figures at all. The honest version is simpler and more useful anyway. On a cold cache, UV is roughly as fast as your internet connection allows, because there's genuinely nothing else to wait for. On a warm cache, UV is roughly as fast as your disk allows, which is why the first install of the day feels ordinary and everything afterwards feels instant. All of which costs disk space, so let's look at managing it. For commands, and each does something different. dir tells you where the cache is. Clean empties the whole thing, or one named package. Prune removes only what nothing needs anymore. And prune with the CI flag is tuned for build machines, where keeping built wheels is wasteful. The CI variant is worth knowing if you run builds. On a build machine, the cache usually lives in a saved archive, and built wheels are expensive to store but cheap to rebuild, so keeping them is the wrong trade. Prune with the CI flag keeps the downloads and discards the wheels, which means the saved archive gets dramatically smaller. One thing the cache is not is a mirror. UV still asks the index whether anything has changed, using the ordinary caching headers every web server understands. So a cached copy is used because the server said the copy is still current, not because UV decided to stop checking. That also explains a failure mode worth recognizing. If a cached copy ever seems stale or wrong, you don't need to delete the whole cache and start again. Refresh forces one command past the depot, and cache clean with a package name removes exactly that package's entries. And a practical note if your machine is short of space. The cache and your project folders should live on the same file system because hard linking only works within one file system. Put them on different disks and UV falls back to copying, which costs both time and space.
Quick check.
What makes the second UVX run so much faster than the first? Pause the video here and answer it for yourself before I do. Ready? The cache. The parcel is already in the local depot, so nothing had to be fetched or built again. So, to recap, UV keeps what it downloaded and what it built, keyed on whatever identifies each thing. Being compiled, working in parallel, and hard linking explain the rest. And the only figures worth quoting are the ones you measured yourself. Next chapter is for everybody arriving from pip. Every command you already know, translated, plus the places where UV is deliberately stricter. You already know pip. Nearly every command, you know, still works. Put the word UV in front of any pip command you've ever typed, and the command works. Same flags, same arguments, same shape of output. So why bother at all? Because the install that took pip 11 seconds takes under a second and a half here, and because UV catches things pip waves straight through. Welcome back. This chapter is a translation guide for everything you already know, plus the handful of places where UV is deliberately stricter than pip, and will tell you so. Start with the door that looks exactly like the one you came through. Install, list, freeze, show, uninstall. Every one of them exists, and every one behaves the way you'd expect. There's a tree command too, which pip has no equivalent for and which you'll reach for far more often than you'd guess. Then there's uv.venv, which replaces python-m venv and does two things that command never did. First, it names the interpreter it borrowed so you know what you got. Second, it prints the activation line for the shell you're actually in, which saves a search every single time you forget the Windows spelling. Now the pair that replaces a whole separate tool. If you've used pip-tools, this pair will look immediately familiar. Compile turns a loose list of requirements into an exact pinned one. Sync then makes your environment match that pinned list precisely. Both live inside UV already, which means there's nothing extra to install and nothing else to keep updated. And here's a trap that catches almost everybody the first time. Compile prints its output. Compile does not write a file unless you pass -o. So a beginner runs the documented command, sees the result scroll past, goes looking for requirements.txt, and finds nothing there. Those little VIA comments are worth reading, by the way. Every pinned line records who asked for it. VIA rich means rich needed it. VIA-r requirements, .in means you did, which turns a wall of pins into something you can actually audit. One more distinction, and it mirrors Chapter 9. UV pip install adds to whatever is already there. UV pip sync makes the environment match the file exactly, which means anything not in that file gets removed. Install is additive. Sync is exact. Reach for the right one. Now the migration itself, which is genuinely 2 commands. Run uv init on the folder you already have, then uv add dash are pointing at your requirements file. UV reads every line and writes each one into pyproject properly. Point -c at your pinned file as well, and UV keeps the exact versions you were already running, because a migration that changes your versions isn't a migration, it's an upgrade in disguise. The mapping is easy to hold. Your loose requirements file becomes project dependencies. Your pinned file becomes the lock file. And any dev requirements file becomes a dependency group, which is what Chapter 7 called the development group. And finally, the places where UV will not do what pip did. The documentation puts it plainly. UV is stricter than pip and will often reject packages that pip would happily install. None of that is UV being difficult. Broken metadata pip waved through becomes a problem you find weeks later, and later is always more expensive than now. 3 differences will actually bite you. UV has no -- user install. UV ignores pip, onf, and the pip index environment variable, using its own settings instead. And UV wants a virtual environment rather than installing into the system Python. And here's one that surprises even experienced people. Upper bounds on requires Python are ignored entirely. If a package claims to need Python below 3.12, UV treats the claim as advice rather than law, because such upper bounds are almost always wrong, and they age very badly indeed. One habit worth changing while you're here. In the pip world, you'd activate an environment and then type pip install. With UV, you can skip the activation entirely because UV finds the environment for you, which is Chapter 8's lesson arriving in a place you didn't expect it. A word on when to use which interface, because having both can be confusing. The pip commands are a bridge, perfect for an existing project, a quick experiment, or a script somebody else wrote. For anything you'll maintain, use the project commands instead, because those give you the lock file. Finally, 2 things you'll want on day 1 of any migration. UV pip check reports anything inconsistent, exactly like the pip command from Chapter 0. And UV pip freeze still prints what's installed, so you can compare against the file you started with. Quick check. You run UV pip compile on a requirements file, and then look for the output file. Is it there? Pause the video here and answer for yourself before I say it.
Ready?
No, compile prints to your screen unless you pass -o. So, to recap, every pip command you know works with UV in front of it. Compile and sync replace pip-tools outright, and compile prints unless you ask it to write. And UV is deliberately stricter, which costs you a refusal now instead of a mystery later. Last chapter next. Turning what you've built into something anybody in the world can install with 1 command. Your code works. Now, let anyone in the world install it with 1 command. UV build, and 2 files appear in a folder called dist. Read the second line of that output carefully, because UV is saying something people get wrong constantly. Which of those 2 files does the other one come from? The wheel is built from the source distribution, not alongside it. Welcome back, and welcome to the last chapter. This one turns the project you've built into something anybody can install, and it does that without ever putting a secret on screen. Start with what those 2 files actually are, because they do different jobs. A source distribution is your code, packed up. Anyone installing from Instast has to build a package on their own machine first, which takes time and sometimes needs a compiler they haven't got. A wheel is the built result, ready to unpack straight into a folder, which is exactly why installing from a wheel is nearly instant. Reading the file name tells you a lot. Invoice_app is the package. Not .1.0 is the version. py3 means any Python 3. None means no C extensions. And any means any platform, which together say this will install absolutely anywhere. Before publishing anything, 2 things need checking. The first is easy to forget and embarrassing to get wrong. If your project points at a local folder or a Git branch while you're developing, that pointer must not travel into the published package, because nobody else has your folder. Building with no sources makes UV resolve exactly as a stranger would. The second is the version number, and UV manages that for you. UV version prints the current one. Bump takes it forward by major, minor, or patch. Dry run shows you the arrow without changing a single file, which is the safest way to check the bump does what you meant. A quick word on what those 3 words mean, because choosing wrongly annoys everybody downstream. Patch is a fix that breaks nothing. Minor adds something new, while keeping everything that already worked working. Major means you broke something deliberately, and every person depending on your package now has to read the release notes. And now publishing, carefully because this is the step involving credentials. UV publish uploads what's in dist authentication comes from an environment variable, and I want to be explicit here. You set that variable in your own shell, and it never appears in a command, in a file, or on anybody's screen. What you see here is the variable's name, never its contents. Practice on test pypi first. It's a completely separate copy of the index, built for exactly this, and a mistake there costs nothing at all. Point publish at it with the index flag and you get the whole experience without touching the real thing. There's a better option than a token if you publish from a repository. Trusted publishing lets your CI provider prove who it is directly to the index, which means no token is created, stored, or rotated, and a secret that doesn't exist cannot leak. Then verify, because publishing is not the same as working. Run your package from a completely clean environment, with no project around it at all. If the import succeeds under those conditions, a stranger with nothing on their machine can install what you published. 2 build flags are worth knowing before you need them. You can build only the wheel or only the stist, which matters in a build pipeline where the 2 are produced by different jobs. You can also build a package that lives in a subfolder of a larger repository. One rule about published versions catches people badly, so let me say it plainly. A version, once published, is permanent. You cannot re-upload not 0.2.0 with different contents, ever. If you got it wrong, the fix is always to publish a new version, never to try to replace an old one. One last thought, for whoever installs what you publish. Everything from Chapter 9 applies to your users as well. Their lock file records the exact bytes of your wheel. So the more carefully you version, the less painful your package becomes to depend on. Last quiz of the course. What does UV build with no sources actually protect you from? Pause the video here and think it through before I answer. Ready? From publishing something that only resolves on your own machine because of a local path. So that's the whole course. You started with a shelf that everything fought over. You now have a project with its own shelf, an exact list of what's on it, a Python version pinned to it, and a package anybody in the world can install. 13 chapters and no ritual to remember. So, to recap, UV build writes a source distribution and then builds the wheel out of it. Build with no sources before publishing, so a local path can't escape into the world. And keep every credential in an environment variable where nobody can read it over your shoulder. That's the course. Go and make something, and if it helped, the whole series is right here waiting for the next person who needs it.